right, today we're going to discuss derivatives a little bit more, including drawing derivatives, which is kind of a weird concept, but we're going to practice it some more tomorrow in class, and hopefully we will get the hang of it before too long. So, when I go to graph a derivative, there are certain things that I want to look at. If you notice, the slope at all three of these points is 0. That matters because up here, our points are f of x, or x f of x, or x y, right? Down here, it becomes x f prime of x, or x slope from the picture above. That's what we're talking about. So, if I know the slope is 0 here, I'm going to put a point at 0 at that same x value. My slope here is 0, so I'm going to put a slope at 0. And right here is 0, so in the middle, a little past 3, I'm going to put a slope of 0. So the slopes are 0 at all three of those locations. I'm going to mark those here, here, and here. Sometimes it might help to kind of divide your graph by that so we can talk about the different areas. Now let's look at the slope over here. If you notice, that slope is negative. And it's big negative numbers, and then it kind of becomes more gradual and smaller negative numbers. So big negative numbers, smaller and smaller negative numbers. Kind of confusing, but not so bad. Let's look between these 2 points. Small positive, because it kind of gradually gets bigger. Bigger positive, smaller positive. So that portion of our graph will be small positive values, bigger positive values, smaller positive values. This chunk here, if you notice, small positive to bigger to smaller positive, or negative, I'm sorry, those were all negative, so small negative to bigger negative to smaller negative. And after this point, all of this starts with small positive to bigger positive, small positive to bigger positive. So you are translating your y values from your y value to your slope. We'll talk about it more tomorrow. You're probably going to want to pause this video, rewind a little bit, and listen to me explain that again, because it is our only example in the notes. Now, sometimes we can use a table of values to construct a derivative. The rate of inflation in percents in the United States as a function of time. So I prime of t would mean the rate of change of inflation in a particular year. Now, if we're finding I prime of 1991, I want the slope here, and we've done this before in section 1.8. We tried to decide how can we find the derivative at a point. Well, if possible, we use a point on either side. If not possible, you use the best you can. So if it's the last point in your list, you would use that point and the point before it. If it's the first point in your list, you would use that point and the point after it. So do your best to use the points on either side if possible. So I'm going to be using 1989, 4.8, and 1993, 3.0, and I'm going to find slope. So, y minus y over x minus x is going to give us 1.8 over negative 2, negative 4, I apologize, negative 4, which is equal to negative 0.45 per year, percent per year. Negative 0.45% per year. On the back, it says, find a formula for f prime of x. Again, How do we find a derivative? It is the limit as h approaches 0 of our difference quotient. F of x plus h minus f of x all over h. So in this case, f of x plus h is going to be x plus h cubed minus x plus h. We're going to subtract f of x, which is just our function. Make sure you put it in parentheses. That negative will need to be distributed. Now, you can FOIL this first term 3 times, or you can memorize a formula that's on the cardboard sheet in the back of your book. And the top simplifies to this polynomial. You notice at this point our x cubed cancel out and our x's cancel out. We need that h at the bottom to cancel out. If you're doing the difference quotient correctly, everything that doesn't have an h should cancel so that we can take an h out to cancel with the denominator. So I'm going to pull out an h. We have 3x squared plus 3xh plus h squared minus 1 all over h. My h's cancel. We're not approaching infinity. We'll get to that later. We're approaching 0. We can plug that 0 in for my h's now, and we get 3x squared minus 1. And this is f prime of x. It is the equation for the derivative. Now, we can get derivative notation in lots of ways. Y prime, dy dx, df dx, lots of things. The ones you're going to see the most often are these. The other 3, and this last one here, you won't really see a whole lot until we get later on in the year, but it will come back. The other 3 could show up, won't very often, but they're there if you're not sure what your notation means. So if the derivative can be found, then the function is considered differentiable at that point. So if directions say differentiate, that means find the derivative. And right now, the only way to do that is the limit as h approaches 0 of the difference quotient. That definition 2 is the only way that you can get an equation. Definition 1 no longer works if we need an equation because it can only be the value at a point. So, when is a function differentiable? A function is differentiable if if f prime of a exists. That makes sense. If the derivative at a exists, then it's differentiable. It is differentiable on an open interval, a to b, or a to infinity, or negative infinity to a, or negative infinity to negative infinity, if it is differentiable at every number in the interval. So, if a function is differentiable at a, then it is also continuous. So if you look at a graph and you see that it's not continuous, then it's not going to be differentiable. But some things that are continuous are also not differentiable. We'll get to that in a little bit. So, when does a function fail to be differentiable? Well, it fails to be differentiable at a corner, cusp, or kink in the graph. So if your graph turns sharply, or if your graph comes to a point like that, those are not differentiable at that particular corner. You cannot find the derivative. A discontinuity, something like a jump or an asymptote would be another discontinuity. And finally, a vertical tangent, something like this where it goes vertical just for a split second, or where it comes to a point that has a derivative that is vertical here or here. So if it goes vertical at all, that could be where. So Where is the function f of x equals the absolute value of x differentiable? Well, we know it looks like this. So that means that it's differentiable everywhere except here. So it would be differentiable from negative infinity to 0, not including 0 because it's not differentiable at 0, but it is just before, and 0 to infinity would be where that function is differentiable. So we'll talk more about differentiable tomorrow in class. Come with questions.